Okay, so we just did specific heat of a metal. We just did the lab for that, which is where we took some water, we took a metal, we heated the metal up in water. It got to about 100 degrees, right? So the metal was initially at 100 degrees, and then we put that hot metal into a cup that had some water in it that was at room temperature, right? So we started at 100 degrees. The cup that had water in it was about 20 degrees, right? So it was pretty cool. Now, just off the top of my head, before we did the lab, I would have expected the water in that cup to go from 20 a lot higher than it did, maybe halfway up to 100, right? Because the metal was 100, the water was at 20, so it should have gone to like maybe 40, 50, 60, something like that. But it barely moved, all right? That's the kind of thing that we're learning about in this section. Why did the water temperature not move much? Why did the metal temperature go down so much? And this brings us to properties of specific things. You had either brass or aluminum. Both of them are metals, and metals don't hold temperature. They don't hold their temperature, their heat very well. They like to get rid of it, or they'll gain it very quick. You see this when you boil water on the stove. So if you've ever put a pan on the stove, put water in it, start heating it up, the pan itself gets really hot fast, but the water inside might still be cold for a while, right? If you've ever made anything. So that's kind of what's going on in here. Water has a relatively high specific heat, which means it takes a lot of energy to heat it up. The reason for that is because of the hydrogen bonds that hold it together. To make water heat up, you have to first start breaking those hydrogen bonds. Metals don't have hydrogen bonds, so they'll heat up a lot faster, all right? So when we're talking about numbers, iron is a very low number, all right? So it's 0.4. Iron heats up very quickly. Aluminum heats up very quickly. Brass heats up very quickly. So most metals that we think of, they'll heat up very, very quickly. And then water takes a while because of those hydrogen bonds, all right? And that's kind of what we saw in this. By the metal temperature going from 100 all the way down to 25 or 26 or whatever your final temperature was for it, that showed that metal lost its heat energy very quickly, and the water absorbed the same amount of energy, but it didn't move its temperature much. Now remember, energy has to be conserved, just like, the conservation of mass. So the hot metal lost just as much energy as that water gained, but the water only raised its temperature a very tiny amount because of this idea of specific heat. Okay, so that was kind of like what happened in here. Now everything has a specific heat, and it's just like density, so every substance has a value, doesn't change. So water's is that 4.184, iron is 0.4. You guys, your goal today was to figure out what either aluminum was or brass was, all right, and see how close you could get to it. So that was kind of our goal. Now to solve these problems, there's a lot of variables, but you know all of this information. For example, the specific heat of water doesn't change, so we know that that's always going to be this number right here with all the units. The mass of water, you found that out when you did the lab, right? That was line number 1, the mass of the water in the styrofoam cup. And then number 2, this is the only thing that's kind of complicated, the change in temperature. So this would be the final temperature minus the initial temperature of the water, all right? So for the water, the final temperature of the water is the same as the final temperature of both of your things. So that was the one that went up a little bit. That was number 5. And then your initial temperature of your water, that was number 2. That was your temperature of your water in the beginning. So when you subtracted that, then you have your 3 variables filled in here. And we're going to do an actual example, so don't worry if you're not following me. We'll go through it with numbers in a second. But you'll just kind of multiply these 3 together. You'll get a number on this side. Over here, this is what we're looking for. So this is going to stay our variable. So this is kind of like our x. We're going to solve for C metal, the specific heat of the metal. You know the mass of the metal because you found it on the balance, right? That was number 3. And then you also can figure out the change in the temperature because this was your final temperature, which these final temperatures are the same, right? That was number 5. And then your initial temperature of your metal, though, that's number 4. So that was around 99, somewhere around there. That was kind of like our 99. So now you'll have 2 numbers you can multiply, and then you have a variable. You have 3 numbers you multiply together. You just solve for this x or this solve for this variable, and then you'll have it. You'll have the specific heat of the metal, all right? The only weird thing is specific heat can't be negative, so if you get a negative number, you just take the absolute value of it, all right? All right, so let's go through my example. My numbers are a little bit different than yours, but while I'm doing this, you can plug your numbers in as well, all right? So let's check this out. This just gives you more information about what everything is. So M is the mass, the change in temperature, this is the change in temperature and how you calculate it. So all that information is in your lab, so you can kind of go along with it. So let me write down my equation, and then we'll get going. So I have C H2O times the mass of H2O times the change in temperature of H2O. This is everything on the left that we just kind of talked about. Equals, and then it's the same thing. It's Cm delta T. Cm delta T. But now we're talking about it for the metal. So I'm just going to put an M down here so I know it's for the metal. And then we have our big M for the mass of the metal. And then we have our change in temperature for our metal. Oop. So the variables are the same here. Whatever the water absorbed, the metal lost. That's why you can make them equal to each other, because there's a conservation of energy, right? Okay, now let's fill in some numbers from our lab. We know that C for water is always 4.184 joules is our temperature for energy, divided by grams times degrees Celsius. So that's the unit for specific heat, all of those three things. That's the same for everyone. Our mass for our water is going to be different for each of us. So it's your average for number one, right? The mass of our water. So my average is 97.32. Yours might be slightly different. It's probably close to 100. Right? Probably we should all be close to 100 with that, but put your number in. And then the change in the temperature. My final temperature is number 5. My average, I just made it easy. I just made up a number. I made it 30. And then my initial temperature for my water, I made 24.91. Your initial temperature should probably be around there too, maybe 25, 26, because our room's warm today. And I'll pause for a second if anybody needs some help with that. Okay, on the other side, we don't know this, so we'll leave it the way it is. I don't like to just put an X there. I like to keep it whatever it is. So that's why I wrote Cm for specific heat of the metal. We know the mass of the metal. I just made this up, but this is your number 3. So mine is 34.19 grams. And then my change in temperature, remember it's final minus initial. So my final temperature is the same as over here, so minus 30. And I got this from line 5. Minus my initial temperature of my metal was probably close to 100 degrees, right? So mine was 99.41. This was your boiling water, whatever your boiling water temperature was. That's what this is. All right, so fill in your numbers. I'm gonna cross some stuff out. Like we have grams here and grams down here, so they cancel out. Celsiuses, they all cancel out. I have them on the bottom, and then when you subtract, they'll just be one of them, so they'll just be there. And then I'm going to do the subtraction first, and then multiply these 3 numbers together. And that'll give me, which your number is going to be different, 2,072.58 joules, because joules is the only thing that's left, and that's on the left. And then on the right, I'll I'll subtract these first, and then multiply it by the 34, and that'll give me negative 2,373.13, and the only units here are grams and Celsius. Now also we have this Cm, right? That comes down as well. All right, now we have Cm over here and a number. We have a number, we want specific heat of the metal by itself, so I'm going to divide this on both sides. So we'll divide negative 2373.13 grams times degrees Celsius on both sides. Grams Celsius. Okay. So the units don't cancel out. You're going to keep all of them. There's joules, there's grams, and degrees Celsius on the bottom, which makes sense because specific heat has all three of those. We'll plug that into our calculator. It'll give us a negative number, but remember, we're going to take the absolute value of it. So when I do mine comes up to being 0.8734 joules divided by grams times Celsius. And I'm just going to 4 sig figs because a lot of these up here have 4 sig figs for it. So we can just round to 4 sig figs, that's fine. All right? And that should give you a number, which is going to be different than mine because, again, I made up my stuff. But there you go. That's how you figure out your specific heat. Now, this is the experimental. At the bottom of the paper, it says, all right, if you had aluminum, it should be 0.9. If you had brass, it should be 0.38. You're then going to figure out your percent error to see how close you were using whichever metal you had. And the silver-looking metal, that's aluminum. And then the, I guess, goldish kind of looking metal, that was brass, all right? And that's how you do that.